All right, folks, so based on what we were doing in that Desmos activity, if you were looking at this function, you would probably say that we have x-intercepts where? At +1 and at -5. So I'm going to go ahead and put points there. At -1, sorry, at +1. This is how not well I'm feeling. Ignore that point. So at +1 and -5. So we know some exact points based on those patterns we were seeing on Desmos. But if I were you, I'd be going, but why exactly are the signs switching? And why does that relationship work that way? I want to talk for a moment about the structure of an x-intercept. And this kind of goes back to Unit 1 where we did all that linear stuff. An x-intercept is a number and 0. So if I take 0 and plug it in for f of x or y, we would get 0 equals x minus 1 times x plus 5. Now I plugged in 0, and normally linear-wise, we would get something that we could easily solve. With quadratics, it's a little bit different, so we're going to get into one of our properties that's going to help us with solving. Folks, let's say, and you don't have to write this down, that I have a times 4 equals 0. What does a have to be? It has to be 0. What if I have -3 times b equals 0? What does b have to be? It has to be 0. So then what if I have c times d equals 0? What do we know about c or d? One of them has to be equal to 0. So the only way for me to get a product of 0 is if one of the factors or one of the multipliers is equal to 0. So either this one is 0 or this one is 0. So folks, we call this, and this I would like you to write down, the zero product property. Product, which means multiplication, and 0 because that's what I'm getting for the product on the right side. So here, if I have this factor times this factor equal to 0, what does that tell me about the two items similar to what we had with C and D? It means one of these has to be equal to 0. So if we set x minus 1 equal to 0, then we would see that x is equal to +1. If we set x plus 5 equal to 0, we see by subtraction that x is equal to -5. So folks, we're going to get heavily into the algebraic solving side of this in the next unit, but I want you to know that that is why when we are in factored form, we can switch the signs to get my roots. So for right now, you can just use the shortcut and say, hey, if I switch the signs of those factor numbers, we're going to automatically get my x-intercepts on my graph. So we now know the x-intercepts. What about the y-intercept? We don't normally care about the y-intercept when we're solving, but it is an easy point that we can sometimes graph. So let's see if we can find the y-intercept. And if my x-intercept is a number and 0, then my y-intercept is 0 and a number. So instead of plugging in 0 for f of x in solving, we're going to plug 0 in for both of these x's and solve for what y is equal to. So y equals 0 minus 1 times 0 plus 5. So to find the x-intercepts, we plug in 0 and use the 0 product property to find those x values. For the y-intercept, we plug in 0 for x. It's the same concept as the cover-up method. It's just, it's not as friendly of solving because these equations are a lot more complicated than linear ones. So what's 0 minus 1? Following PEMDAS, doing what's inside the parentheses first. -1. What's 0 plus 5? 5. So then y is equal to -5. And as a coordinate, this would be 0, -5. And that is my y-intercept. So now we have 3 exact points on our graph, which is way better than trying to do like an input-output table for this. So those are 3 exact things that we know about our graph. But doing what we did yesterday, there are actually a few more things that we know as well. Let's talk about the degree. Now, even pre-calc students sometimes are tempted to look at this and say that the degree is 1. But with all the problems that we've done with degree so far, those equations have been in standard form. So the degree is the highest exponent, but it's only when the equation is in standard form. When you are in factored form, I'd like you to write this down, for factored form, the degree is the sum of the multiplicities. And I would put a big important box around this. So for factored form, the degree is the sum of the multiplicities. So for factored form, the degree is the sum of the multiplicities. So we better define what multiplicity is. Multiplicity is the power or exponent of each factor. The power of each factor. So over on the right side here, this would have a multiplicity of 2. What about the x minus 5 factor? What is its implied power? It's 1. So that means this would be draw degree stuff over here. That would mean our degree for this polynomial is degree 3. We took 2 plus 1 to give me the degree. Now over on this one then, this factor has a multiplicity of 1. This factor also has a multiplicity of 1. So what's our degree? 2. And it's important to have this fact memorized because the alternative would be to change this function to be in standard form. So if I have y equals x minus 1 times x plus 5, how do I change this into standard form? We would need to carry out the multiplication so that it's all addition and subtraction. So FOILing means I take the front terms times each other, or the first terms times each other, which gives me x squared. Outside terms times each other, x times 5, 5x. My inside terms times each other, -1 times x, -1x. And my last terms together, -1 times 5, -5. How many of you guys remember FOILing from Algebra 1? Remember that acronym? Give me a hand raise if you're like, yep, I remember seeing that at some point. Okay, good to know. So then if I simplify this, we would get x squared plus 4x minus 5. So take a look at this problem, which is now in standard form. Is this a degree 2? Sure is, but we don't want to have to FOIL every single time. It's kind of a lot of work, and I definitely don't want to have to do this one of x minus 1 times x minus 1 times x minus 5. That's a lot of stuff to multiply together. So the shortcut just says take your highest power of x and its multiplicity, highest power of x and its multiplicity, and multiply those together or add the exponents to give you x squared. So conceptual wise, that's what's happening in these problems, but ultimately this is why we can just add the multiplicities to show me what that highest power or degree would be in standard form. So we've got a degree 2 and we've got a degree 3. What else do we know about this one? It's even multiplicity. And what about the leading coefficient? Is my leading coefficient positive or negative for this one? It's like we have an implied 1 here, and 1 is positive. So if I have a positive leading coefficient, what do we know about the end behavior? If it's even and it's positive, what do we look like? Show me with your arms. What's my end behavior look like? Up and up. So even degree functions go in the same direction, and because the leading coefficient is positive, that right arrow is going to go up. So I know my end behavior is up and up. So now, not only do we have those 3 exact points, we also know that my end behavior is going to be an arrow up here and an arrow over there. So we're starting to get a pretty good looking sketch from this. Now, the last thing that multiplicity tells us, and this goes back to what we saw on that Desmos thing, is how a function behaves at each x-intercept. If the multiplicity is 1, then the function crosses at the x-intercept. If it has a multiplicity of 2, it's gonna bounce at the x-intercept. And how I remember this is even is 2 and odd is 1. So cross is going to go straight through, and bounce is kind of like a 1-2 step, like off of a trampoline. So let me show you what I mean. So it takes 1 step to jump down on the trampoline and a 2nd step to pop back up. So that 1-2 step is how I remember that I need 2 movements to bounce off the axis. Or you can think of cross as 1 syllable and bouncing as even. Yes? Yep. Odd is 1 syllable, even is 2, so you can think even of it hitting the x-axis, if that helps you. So even as it bounces off the x-axis. So folks, with this in mind, we know that this one has an odd multiplicity of 1. This one has an odd multiplicity of 1 as well. So at those x-intercepts, we are going to cross and cross the x-axis. So I like to put C's by those for cross. Let's go back in here. So now we can get a pretty decent sketch based on these key features. So we know that the end behavior is going to be going up and up. So I'm just going to draw an arrow over here and an arrow over there, showing my end behavior. And now I am going to work it through these points based on what we have for the behavior at those intercepts. So I'm going to cross right through that point. I'm going to hit that y-intercept. I'm going to cross at that point and then curve up through that other arrow. Is this the definite way that function looks? No, but it's a fairly decent picture. Now, I'm going to draw another possibility. Maybe it looks more like this. It crosses, it goes way down there. It comes back up, and maybe it just goes straight through. Both of these are possible sketches. Let me show you what wouldn't be a possible sketch. So we're going to draw this one in red. What if I come on down and I do a little wiggle there and I make a W? Does anyone know why that red line is not possible? If this is a degree 2, how many turning points can we have? Only one. One less than the degree. This red one has too many turning points. It has 1, 2, 3. So put a note that says not possible, too many TPs. Too many turning points. Now, what's nice about this is we can check ourselves on our calculator and see exactly what this should look like. So if I go to my y equals and type this sucker in, we would do parentheses, x minus 1, close off the parentheses. You don't have to put the multiplication sign in between those parentheses. It's implied on paper. It's also implied on the calculator. X plus 5. And if I hit graph, we see that that green one that I drew is pretty darn close to what the actual graph looks like. I can verify my y-intercept. That looks like it's right at 0, -5. And I can also see my x-intercepts here. There's the x-intercept at -5, and there's the other x-intercept at +1. So that's the nice thing about having a calculator is we can kind of verify what this graph should look like, but we have algebraic ways of finding some of these exact features. So let's go ahead and take a look at our next one. So we're going to start with the degree stuff here. I normally start with the degree similar to what we started with yesterday. I just think going in this order with these key features and then doing the new stuff is a little bit easier. So we know that this is going to be degree 3 because of the 2 and the 1 from factored form. If we were to FOIL that out or expand it out, our highest power would be x to the 3rd. So this is odd degree. And what about the sign of the leading coefficient? Is it positive or is it negative? It's negative. So we've got a negative in front of that factored stuff. So we have a negative leading coefficient. So that means my right arrow is going to go down based on the leading coefficient. And my left arrow is going to go in the opposite direction so that my end behavior does the little disco dance. So that's a review of the stuff we did yesterday. The degree, although we're finding a little bit differently in factored form, even or odd, and then the sign of the leading coefficient. Now, for the new stuff, what are my x-intercepts? So we've got x minus 1 as a factor. So x equals 1. is an x-intercept. What's my other intercept? If it's x minus 5 as a factor, it's x equals 5 as the x-intercept. And let's see how our graph is going to behave at these x-intercepts. Our multiplicity of this factor is 2. So 2, we think of that 1, 2 step, which is a bounce at x equals 1. So even multiplicity will bounce. Odd multiplicity, which we have here, is 1. That will cross. So multiplicity even, it bounces. Multiplicity odd, it crosses. So I'm going to put a B by the x equals 1 and a C by the x equals 5. B for bounce, C for cross. Let's find the y-intercept. So my y-intercept is 0 and a number. So we're going to take 0 and plug it in everywhere we have an x. So y equals negative 0 minus 1 squared and 0 minus 5. And we're right back at it with PEMDAS. We start inside the parentheses first. So 0 minus 1 is negative 1. 0 minus 5 is negative 5. Now I know that it's really tempting to change that into a plus sign, but why can't we do that? Exponent, you have to take care of the exponent first. So negative 1 times negative 1 is a positive 1. And now we can multiply. Negative times 1 is negative 1 times negative 5 is a positive 5. So boom, my y-intercept is 0, 5. So using those 3 exact points and this key information, let's see if we can draw a sketch of our graph. So I'm going to go ahead and draw an arrow up here. And I'm going to show it curving down into that y-intercept. And then at this one, it's going to bounce back up. And then it will cross. Bounce and cross. Let's verify that we're all good with our turning points. If this is degree 3, how many turning points can it have? It can have at most 2, and sweet, that's exactly how many we have. Are there other ways we could draw this? Sure. Maybe it's way out here and then curves down this way and then bounces and goes way up here and then crosses. But as you can see, it's still got to bounce at that x-intercept. It still has to cross at that one. And it still has to go through the y-intercept. So let's see how close we are using our calculator. Little negative x minus 1 squared and x minus 5. Does it look close to what we have? Little bit closer to the green one, so it does get a little bit higher than what I had on that purple one there, but we are just sketching these. But what we're showing is, without our calculator, we were able to look at the equation and use this key info to get a pretty good idea of what that graph looks like. So let's go ahead and, you may be wondering, why did we not fill anything here? We just kind of vaguely talk about this even in pre-calc, so you can draw a little cloud around this. This is not something that you need to know. You have a multiplicity of 3. It still crosses, but it is more of a wiggle, like a cubic function. So instead of just kind of crossing through straight, it sort of curves into it and then curves back out of it. I'm not going to be fussy about that at all. You can interpret those those multiplicities of 3. You can interpret those as just crossing. Okay, so we're going to go ahead and go into the guided practice next. And actually, before we do that, let's go ahead and take a bathroom break, phone break.